We're now going to talk about a very special random variable called the Poisson random variable. And it's named after a French mathematician. And what's really unique and special about this particular random variable is that unlike the previous special discrete ones that we've looked at, the binomial, negative binomial, geometric, hypergeometric, and so forth, those come from a very specific, well-defined type of experiment. The Poisson random variable is a lot more general. And before we start writing anything down, let me just say a few things, give you an example of a type of process to which this random variable can be applied. So let's say you know that during an hour period, on let's say a Friday afternoon, let's say from 6 p.m. to 7 p.m., on average, you would observe 5 visits to an emergency room, right? So you know the average number of visits for that hour period. Well, what if you want to know, like in that hour period, what is the probability that I will observe more than 7 visits to the emergency room, or fewer than 3 visits to the emergency room, right? And all we're told is that, we know the average number of visits to that emergency room. But not only that, what if instead of just an hour period, what if you want now, let's say the time interval from 6 to 8, right? What is the probability that in that 2-hour period, right, you'd observe more than 12 visits to the ER, right? Or what if in that 2-hour period, what is the probability that you observe no visits to the ER? How likely is that? Again, can we get to that level of detail just by knowing the average number of visits for a fixed interval? And it turns out we can, and it's through this Poisson random variable. Now, before we define like the PDF of this, we need to define what's called a Poisson process. These are the properties that define when a Poisson random variable can be applied, right? All right, so let's define what a Poisson process is, list the properties, and just say a few things about them. So a Poisson process, right, has the following properties, right? So first property, well, let's say what it counts. So a random variable x is the number of times an event occurs, right? And x can take on values 0, 1, 2, 3, and so on. So right away we see that this is countably infinite, right? And the events here could be with respect to time or space, right? So, the interval right, may be of time or space, right? So another example, with this would be, let's say you are analyzing a certain stretch of a highway for potholes, and you know that on average per mile you might see, I don't know, 5 major potholes. Then you might ask yourself, well, if I continue on this highway, what is the probability in the next mile I would observe 6 potholes, or fewer than 2 potholes, or no potholes? So that's what we're talking about when we say space, right? So it could be a time interval with my ER example, or it could be a space interval with my highway example. So you can just see the variety of situations to which this Poisson random variable will apply. All right. So the second one, the occurrence. Right. So the occurrence of one of these events, is independent, and this is key, right? Is independent of other events occurring. Right? So the fact that I observe a pothole right now is not going to affect whether I observe it in the next mile or 2 miles or so, right? Same thing. If I observe a person entering the ER at this instant, then it doesn't affect the probability of someone else arriving or not arriving at the ER, let's say, in the next hour or 2 hours, right? So we have independence there, and that's key. And the average rate, right, and that's the average that I referred to. So the average rate of occurrence, so that's the either 5 per hour or 10 potholes per mile. So the average rate of occurrence, let's see, again, is independent, right, of any occurrences. So it doesn't change, right? So for us, this average rate is going to be a constant, right? Right? So this rate will be constant, right? However, it's proportional. So the average rate of occurrence is proportional to the length of time or space, right? So for the average rate of occurrence is proportional to the time or spatial interval. Right? So going back to my ER example, if, for instance, you say, okay, we observe, 5 visits per hour, then proportionally we would expect on average 10 visits per 2 hour, right? Or on average 2.5 visits per half an hour, right? So that the whole idea, this proportional is really key. You can adjust your rate, right, based on the interval of interest, right? And then the fifth one, which is, again, they're all very important. They all factor into this model that we're building. And the fifth one is this, that 2 events cannot occur at the exact same instant. So they cannot occur simultaneously. Right? In other words, in a very small subinterval, Again, and this could be an interval of time or space. So subinterval, an event either occurs or does not, right? So an event either occurs or does not. So this fifth one here, it almost sounds like on a, let me say it this way, on a microscopic level, a Poisson process kind of looks like a binomial process, right? Where you're just you know with the binomial you have two possible outcomes. Either something occurs and we might deem that a success, or it doesn't occur and we deem that a failure. So what this is saying, if you were to take a microscope and put a Poisson process under your microscope and look at it again like at this microscopic level, then it would look like a binomial process going on there. And there is a very direct relationship but with the binomial and the Poisson, but it involves quite a bit of limits and discussions like that, which we won't get into, right? But there is, based on this fifth property here, there is a connection between the Poisson process and our binomial, right? Okay, so with this in mind, let's now define what the discrete Poisson random variable looks like, right? And what is its PDF, right? So if the average rate of occurrence of a Poisson process is, and we typically use lambda, right? Well, first, this is how we write it. We say that x, our random variable, which counts the number of occurrences in whatever interval is defined, we're going to define it like this, and that's our little tilde. So x follows or is distributed as a Poisson, and we're just going to use a big P for Poisson random variable, and with parameter lambda, and that's it, right? So there's one parameter that defines a Poisson process, and all it is, it's that average rate of occurrence, right? So this is how we're going to denote it. Now let's write down what the PDF is, and then I'll state the results for the mean and the variance like we've done for the other ones. So our PDF, it turns out it's actually fairly simple to work with, but it is lambda raised to the x power and then times e to the negative lambda divided by x factorial, right? So this is our Poisson PDF, and as we stated earlier, the sample space for this is countably infinite. So it starts with 0 because it is possible that you observe no events occurring. So no people visiting the ER, no potholes in a given stretch of the highway, or you could observe just one event or two or three or again dot dot dot, right? So it's another example of a countably infinite random variable, right? Now, it turns out for this particular function here, even though it looks fairly simple, we don't have a nice closed form formula for the CDF. But however, we do have tables that we can utilize for the Poisson CDF, and it comes with certain values of lambda and certain values of x. It can't possibly list all the values of x because our sample space here is countably infinite. But it gives some commonly used values of lambda and some of the typical values of x. Now, if we encounter a problem that's not in the table, then we would have to come back to our PDF, and if we need to find cumulative probabilities, then we're going to have to do the summation by hand, right? All right, so that's the PDF, and unfortunately, there is no nice formula for the CDF, but there are very, very nice formulas for the mean and the variance. It turns out, well, the mean, that's already this. It's the average. This is what we would expect during a certain hour or during a certain mile of highway, right? So it turns out that the mean for the Poisson random variable is exactly your lambda. And with a bit of calculus and some infinite series, you can show that the variance is also lambda, which is so convenient, right? So no super complicated formulas for the mean or the variance. It's the exact same value as your parameter, which then makes it easy for us to write down the standard deviation. That's just going to be the square root of lambda, right? So as far as the parameters, doesn't get much easier than this. All right. So let's do a simple example of the Poisson random variable. And in this case, what I'm going to do is just look at a couple examples that utilize exact probabilities, and then in a subsequent video, we can see what the table looks like and how we can utilize it, right? So here's our example. And suppose we have the number of customers arriving at a grocery store. I seem to like grocery stores, right? So at a grocery store follows a Poisson process with lambda 10 customers per hour. So lambda equals, and here it's 10 customers per hour. All right. So and that's all we have to know. Two things we need to know to use this formula. That it's a Poisson process, and we're told what the average rate of occurrence is, right? So in this particular grocery store, they get about, on average, 10 customers per hour. Let's see part A. So part A is going to say find the probability. So find the probability that there are two customers, right? So we have two customers that enter the store or visit the store during this interval, let's say 10 a.m. and let's make it a short interval, 10:20 a.m., right? Okay, so here's our setup, and so let's define. So let x represent this. So let's solve this one. So let x represent the number of customers during this 20-minute period. So the number of customers during 10 a.m. and to 10:20 a.m. right? So we know it's going to be Poisson. The trick, though, is that this is a 20-minute time interval, whereas the average is given per hour, right? So basically, it's going to be Poisson, but my lambda isn't going to be 10. I'm not going to use 10. The average rate that we would expect for a 20-minute period will be 10/3. It will be a third of the hourly rate, right? So 10 over 3, right? So your lambda doesn't have to be, it certainly doesn't have to be a whole number. As I said, it's an average, and we know an average can certainly be fractional, right? So 10 over 3, and let's write down the PDF for this, right? So it's lambda to the x, so it's going to be our 10 over 3 to the x, and then times e to the negative lambda, and then all over x factorial. And again, just for completeness, I'll state the sample space. And the sample space for a Poisson random variable is always 0, 1, 2, 3, dot, dot, dot. So it's always countably infinite, and it always starts at 0. So this model allows for no occurrences or 1 or 2, etc. Right? So in this particular question, we want to know what is the probability that we will observe exactly 2 customers. So the probability that our Poisson random variable is equal to 2, that's where we can use our PDF. So it will be f of 2. So that's 10 over 3 squared times e to the negative 10 over 3 all over 2 factorial. Now if you wanted to simplify this and write it as, like, if you wanted to give it exact in terms of e but reduce it, let's see what would happen. So this will be 100 over 9 e to the negative 10 over 3. 2 factorial we know is 2. So the exact probability is 50 over 9 because the 100 can be reduced by the 2, and then I have my e to the negative 10 over 3. Now if you wanted to give this as a decimal, it's roughly 0.2, right? So roughly 0.2, right? Okay, so that's part A. Let's take a look at part B, which is, again, a slightly different question. Let's look at part B. Find the probability. Right? Again, for both of these, they will be exact, but this one is actually going to be an AND probability. So find the probability that there are 3 customers between 10 and 10:20, right? And 7 customers between 10:20 and 11, right? So now there are essentially 2 random variables that we have. So the first one is the one that we had before, obviously. So let me restate it. So x, again, I'll just restate it, is the number of customers between 10 and 10:20. And we, based on our work in part A, we know that this x is a Poisson random variable with a lambda of 10 over 3. Let me use y to represent the number of customers between 10:20 and 11. Now this is a 40-minute period, so it's going to be 2/3 of our original lambda. So y will also be Poisson, but now it's going to be 10 times 2/3 or 20/3 as my lambda. Right? So let's write down the PDF for both. We already did it for x, but let me do it for x and y. So the PDF for x is our 10/3 to the x e to the negative 10/3 over x factorial. Again, here is our sample space, and then the PDF for y. I'm not going to use f. I'm going to use g, just so that, because they are going to be different functions. So g of little y is now going to be 20/3 to the y power, and then e to the negative 20 over 3, and then here we have over y factorial. And again, y can be 0, 1, 2, etc. And the other piece is going back to our definition of a Poisson process. X and y are independent of each other because these time intervals don't overlap. So what happens between 10 and 10:20 is independent of what happens between 10:20 and 11. So the key here is that since the time intervals are non-overlapping, so since the time intervals are non-overlapping, x and y are independent. So x and y are independent, right? And again, that's one of our properties of a Poisson process. Very, very powerful property. So the question wants, let me write it up, it wants the probability that we have 3 customers in the 20-minute time period, and we want 7 customers in the 40-minute time period, right? And since it's an and since the random variables are independent, I can write this as the probability that x is equal to 3 times the probability that y is equal to 7. And since we have both of these PDFs, so this will be f of 3, and then this will be times g of 7. Now f of 3, that's what we wrote down earlier. Actually, no, we did 2. We didn't do 3. So let's write this down. So it's let me just write it in without reducing it too much. So it's 10/3 to the 3rd power, and then we have our e to the negative 10 over 3. And then this is over 3 factorial. Now 3 factorial is 6. And then times g of 7, so that's 20 over 3 to the 7th power, and then e to the negative 20 over 3. Now I'm not going to write down 7 factorial, it's a big number, but it would be 7 factorial there. And it turns out, so I mean, this, we could certainly write it down exact. It's a little messier than the one that we did earlier. But this is roughly, when you evaluate it, you get approximately 0.0325, right? So roughly 3.25% chance that during the 20-minute period from 10 to 10:20, we will observe 3 customers in this grocery store. and then in the next 40-minute period, we will observe 7 customers in this grocery store. So I mean, it's almost like the possibilities are endless with this Poisson random variable. Even though the properties seem to be rather specific, right? They apply to many situations, and now it's just the tip of the iceberg. So I'm sure you're looking forward to other questions that will involve this random variable. And if that's the case, then your wish is my command. I'll see you in the next video.